Hey everyone, welcome back to another Bytes on a Budget video. Today, I'm putting together another budget gaming PC using some leftover parts I had lying around. Let's start with the motherboard. I'm reusing one that I originally had set up for CPU mining. This is the MSI B450M Pro Max. It uses the AMD B450 chipset and the AM4 socket. It supports first, second, and third gen Ryzen CPUs, PCIe 3.0, and has two DDR4 memory slots. Overall, it's a pretty basic motherboard. There's already a CPU installed, a Ryzen 93900X, but I can't really use it here. It draws too much power for this board's VRMs, and under full load, they overheat and throttle the CPU. When I used it for mining, I had to lower the clock speeds in the BIOS, and even add a fan just to keep the VRMs cool. So I'll be replacing it with a more suitable processor. It's time to install the new CPU. I picked up a used Ryzen 5 3600. It's a 6-core, 12-thread processor that cost me around €30. It's rated at 65 watts TDP, which is quite a bit lower than the Ryzen 93900X at 105 watts. That means this chip should draw less power, run cooler, and keep the VRMs from overheating or throttling the CPU. Unfortunately, while installing the new CPU, I noticed it wouldn't sit all the way into the socket. After taking a closer look, I saw that a few pins near the edge were slightly bent. Not great. I tried lining it up a few times and gently applied a bit of pressure, just enough to get it to slot in without forcing it too much. It seems to be seated properly now, but I'll only know for sure once I power it on. Hopefully, it boots without any issues, but with bent pins, you never really know until you hit that power button. Next up, it's time to install the SSD. I've got a brand new 500GB M.2 NVMe drive. It's a pretty fast one. It supports 4 PCIe Gen 4 lanes and NVMe 1.4 with theoretical speeds of up to 5,300 megabytes per second for reads and up to 4,000 for writes. The catch is my motherboard only supports PCIe Gen 3, which basically cuts the bandwidth in half compared to Gen 4. So while the drive is capable of crazy speeds, we won't quite reach those numbers here. I'll run a quick test to see what kind of transfer speeds we can actually get with this setup. Next up is the CPU cooler. I've actually got two of them lying around. The first one is the Noctua NHL12S, a low-profile cooler that's designed for small form factor builds where space really matters. Because of its compact design, it's rated for a thermal design power of about 95 watts, which means it's not meant for super high-power CPUs, but should handle mid-range chips just fine. It's a solid cooler overall. Noctua is known for great build quality and quiet fans, but this particular one is not ideal if you're planning to overclock or push the CPU too hard. Still, for a setup like this, it might actually be a good fit. I'll check how it lines up with the motherboard and RAM clearance before deciding whether to go with this one or try the other cooler I've got. The other cooler I have is the Be Quiet Pure Rock 2, which is a bit beefier. It's rated for up to 150 watts TDP, so it can handle higher-end CPUs that draw more power and produce more heat. It's also nice and quiet, making it a good balance between cooling performance and noise. Since this CPU is rated at just 65 watts TDP, it makes more sense to go with the Noctua cooler. It's more than capable of handling that heat output, and it fits the build nicely. I'll save the larger Be Quiet cooler for a future project where I'll need the extra cooling power. Now it's time to unpack and install the Noctua cooler. First, I need to remove the default CPU cooler brackets from the motherboard and replace them with the mounting hardware that comes with the Noctua for the AM4 socket. It's a pretty straightforward process, but it's always worth double-checking the alignment before tightening anything down. This cooler can be installed in two ways: the low-profile mode, where the fan sits underneath the fin stack, and the high-clearance mode, with the fan mounted on top. Since I don't have a case yet, I'm going with the high clearance setup for now. It'll give me easier access to everything and a bit more airflow around the socket area. Next up is the memory. This motherboard supports dual-channel memory, but it only has 2 DIMM slots with a maximum capacity of 64 GB. That's up to 32 GB per slot. For this build, I'm using 2 8 GB DDR4 modules running at 3200 MHz, giving me a total of 16 GB of RAM. That should be plenty for a budget gaming setup like this. Because it's a micro ATX board, space is pretty tight. The DIMM slots sit just under the CPU cooler. It's a bit of a squeeze, but there's still enough room to slide the modules in without too much trouble. Once they click into place, we'll be good to move on to the next part. For the power supply, I'm using this EVGA unit rated at 450 watts. It's an 80+ bronze model, so it's reasonably efficient and comes with the usual safety features, like overvoltage, undervoltage, and overcurrent protection. Solid enough for a budget build. That said, 450 watts isn't a ton of headroom if I decide to throw in a more power-hungry graphics card, but we'll come to that later. Let's go ahead and start connecting all the cables to the motherboard, starting with the 24-pin main connector and the CPU power cable. Once those are in, we can move on to the next steps. The Ryzen 5 3600 doesn't include integrated graphics, so I'll need a dedicated GPU for this build. For that, I'm going with the Intel Arc A750. This one comes with 8 GB of video memory, and honestly, it still looks really clean in a build. It launched back in October 2022 as a great value option for 1080p gaming, and it can even handle 1440p pretty well in a lot of titles. Performance-wise, it sits around cards like the NVIDIA RTX 3060 and the AMD RX 6600, which puts it in a pretty sweet spot for budget and mid-range builds. I think it's going to pair nicely with the Ryzen here. Not overkill, not underpowered, just a solid match for what this system is meant to do. Plus, it's always fun to use Intel's Arc lineup, since they've improved a ton with drivers over time. Let's get it installed and see how the combo performs. Alright, the build is officially complete. So now it's time to put it to the test. This is always the fun and slightly nerve-wracking part. So far, things are looking good. I'm able to get into the BIOS, which is always a relief. Before I jump into installing Windows, there are a couple of settings I need to take care of. First up is enabling the XMP profile for the RAM. Without it, the memory runs at a much lower speed than it's designed for. Turning on XMP automatically sets the right frequency, timings, and voltage so we get the performance we actually paid for. It's a quick step, but it makes a noticeable difference. Next, I'm enabling rebar, or resizable base address register. Basically, it lets the CPU access the GPU's full video memory at once instead of in tiny chunks. Intel Arc cards really benefit from this, and it's pretty much required if you want to get the best performance out of them. Alright, with those settings dialed in, the system should be ready for the operating system. Let's move on to the Windows install and see how smooth this goes. Windows installed and booted up without any issues, which is a good sign. Before installing the GPU drivers, I'm doing a quick check in CPU-Z. I'm confirming the CPU and motherboard info, and it shows PCIe 3.0 with a max speed of 8 gigatransfers per second. My Arc card supports PCIe 4.0 and 16 gigatransfers, but for now, it's running at the expected PCIe 3.0 speed because of the board. I also checked the Memory tab. It shows the correct speed, capacity, and XMP profile. And on the GPU tab, I can see the Intel Arc card details, like core clocks, memory size and type, and bus width. Everything looks in order, so next step is installing the drivers. I've downloaded the Intel Arc drivers and ran the installer. A few minutes later, everything was finished. Right away, I saw a message confirming that resizable bar is enabled. which is exactly what we want for this GPU. Inside the Intel graphics software, you can check all the hardware details and tweak different settings for performance and visuals. There's a lot you can play with there, but for now, I'm just leaving everything at default. The goal is to get the system stable first. We can worry about fine-tuning later. Next up, let's move on to testing and see how this setup performs. For the first test, I'm running FurMark at 1440p. The GPU and memory temps climb pretty fast, hitting around 73 degrees on the core and 80 on the memory. Since this card can draw a lot of power, I plugged the whole system into a watt meter. Especially important because I'm using a 450 watt power supply. Under load, the system pulls just under 340 watts, which is acceptable for this setup, though I'd still recommend at least a 550 watt PSU for anyone building something similar. The benchmark finished at 93 frames per second, so this system definitely has enough power for 1440p gaming. We'll take a look at real gameplay in a moment. Next, I ran a Cinebench test to check how the 6-core, 12-thread CPU holds up. I also wanted to see how the Noctua cooler performs when the processor is under full load. The temps looked solid. The CPU stayed under 77 degrees Celsius, so cooling doesn't seem to be an issue here. For the multi-core score, it landed at 545 points in Cinebench 2024, which is right in the expected range for this chip. Nothing record-breaking, but completely on target for a setup like this. So overall, no thermal surprises, stable performance, and the cooler is doing its job. Here's a quick test of the NVMe drive. It supports PCIe Gen 4, but the motherboard only runs at Gen 3. With 4 lanes, that means a theoretical max of about 4 GB per second instead of 8. The drive itself is rated for around 5.3 GB per second reads and 4 GB per second writes. In Crystal Diskmark, we're seeing roughly 3.3 GB per second for both sequential read and write. That lines up with the Gen 3 limit, so the PCIe interface is definitely the bottleneck here. Still fast, just not full Gen 4 speed. Now let's move on to some gaming tests. First up is Doom Eternal at 1440p on Ultra Nightmare settings with ray tracing turned on. The average frame rate sits around 45 FPS, technically playable but not very smooth. The GPU is running at 100%, while the CPU sits just above 40%, so it's pretty clear the GPU is the limiting factor here. Next, I turned ray tracing off. With the same resolution and settings, the frame rate jumps to about 77 FPS, which feels much smoother and very playable. The GPU is still pegged at 100%, and the CPU usage goes up to around 60%. So for this setup, ray tracing definitely pushes the card really hard, but the game runs great at 1440p. Next up is Cyberpunk at 1440p set to high with ray tracing and frame generation off. I wanted to see pure CPU and GPU performance, and honestly, it's not great. The game averages around 38 frames per second. The GPU is at 100%, and the CPU is sitting above 70%. Both are working hard, and the result is barely playable. Turning frame generation on makes a big difference. The average jumps to about 67 frames per second, which feels much smoother. But again, both the CPU and GPU are pretty much maxed out, with the CPU still above 70% on average. So yes, 1440p is playable with these settings, but the system is definitely being pushed to its limits. The last game I tested is Borderlands 3 at 1440p on ultra settings. It runs pretty well overall, averaging around 65 frames per second. The GPU is maxed out the entire time, and the CPU sits a little above 50%, with some spikes here and there. I also noticed the GPU running hotter in this game than the others, climbing up to around 77 degrees Celsius. Switching to medium settings at the same resolution bumps performance up to about 109 frames per second, which is a really nice jump. The GPU is still working hard and running warm, but gameplay feels extremely smooth at that point. After that, I went back to high settings and capped the frame rate at 60 FPS from within the in-game settings, similar to gaming console standards. With the frame cap on, GPU usage drops to around 80%, and the temperature comes down a few degrees. The CPU also looks more relaxed, so the system isn't being pushed quite as hard. So in the end, Borderlands 3 is very playable at 1440p on high settings, especially with a 60 FPS cap. It keeps temps in check and still gives a great experience.
And that wraps up the video. I'll leave the full system specs on screen. Overall, I'm happy with how this build turned out. It can handle most modern games at 1440p with a few settings tweaks, but it's really best suited for smooth 1080p gaming. The total cost for used parts here in Europe is roughly €500, or about $570. If you enjoyed the video, feel free to like and subscribe. Thanks for watching.